Suppose we are flying in a plane and throw a ball outside. Obviously, we see the ball plummeting towards the earth. If we look closer though, we notice that something remains constant for the ball throughout an interval of time. That's right, its total mechanical energy is conserved. However, if we measure the ball's momentum in the same interval of time, it doesn't stay the same. In fact, it's increasing.
Hey, isn't this violating the law of conservation of momentum? Is physics broken?
Before we answer that question, let's look at the ball more closely. If we look at its total mechanical energy throughout any interval of time, it is always constant. This means that the ball is essentially invariant under continuous translation in time. The ball is said to exhibit time translational symmetry. The ball's momentum, however, does not stay the same as it moves through space. The ball is not invariant under spatial transformation and does not exhibit spatial symmetry. We can also look at the expansion of the universe to understand this more clearly.
When light leaves a distant object and travels through expanding space, it actually gets stretched out and its wavelength decreases.
According to the simple formula E equals hf, its energy also decreases.
Wait a minute, do we see a pattern here?
In 1915, a German mathematician called Noether saw exactly this pattern. She worked out the math behind symmetries and systems and found out a relationship between symmetries and physical quantities.
And she did that in her spare time. Anyways, Noether's theorem states that for every continuous symmetry there exists a corresponding conservation law. According to her theorem, different symmetries give rise to different conservation laws.
For example, rotational symmetry gives rise to conservation of angular momentum, and a gauge symmetry gives rise to conservation of a color charge. In the example of the ball, we have already seen that it isn't spatially symmetric, and hence its momentum need not be conserved. It is symmetric in time translation, and hence its energy is conserved. Let's assume a space with just one axis of space and one axis of time. If a body were to move in a trajectory and we applied a transform phi, the body's trajectory would change. If we assume that phi is symmetric, then there should be a conserved quantity. The change in action between t0 and t0 plus tau and t1 minus tau and t1 should be equal in order to keep the net action 0, which gives rise to the conserved quantity dl by dq over dot or canonical momentum.
Noether's theorem is widely considered as one of the most beautiful theorems in all of physics. It's because of her theorem that dark energy, the electroweak model, quantum chromodynamics, and basically the whole standard model is possible. Unfortunately, being a woman in her time was considered a misfortune, and she did not get the recognition she deserved. Even today, her works play an influential role in shaping modern physics. We would not be where we are today without her genius.